Hi, and welcome back to another video on synoptic scale features. And this one is the fourth video on jet streams. So far we talked a little bit about jet streaks and what they do. We talked about the convergence and divergence and the ageostrophic motions that are associated with jet streaks. We talked about the rising and sinking motions. We're going to kind of combine that with fronts now because we know that typically, where you find a jet streak and a jet stream, there's also probably a front pretty close by. Remember that jet streaks and jet streams are a result of horizontal temperature gradients, and those are a result of the structure of a front. So we're going to go through a front and talk about how that influences the jet streaks. So first off, remember this picture? We talked about the cross-section of a front, looking at the cold air to the north and the warm air to the south. You got a frontal zone, a lower portion and an upper portion, and then the tropopause. Remember that the tropopause is lower over the cold air and higher over the warm air. So with that in mind, we're going to put a jet streak on this frontal system. We're going to look at a jet core specifically and a jet streak. The wind moving through this jet core is accelerating and decelerating depending upon what region you're in. So we'll start out with the entrance region. So this is kind of the rear, or if you think of a wind moving from the west to the east, this is the western portion of the jet streak. So the air is coming into the jet streak, and as it comes in, remember, it's accelerating, and that acceleration causes cross-contour flow to the north. So you have divergence in the warm air or to the south and convergence in the cold air to the north. So that means that the compensating motions causes rising air in the warm sector and sinking air in the cold sector. Now this is what you normally expect. You usually expect warm air to rise. Warm air tends to go to higher altitudes, and cold air tends to sink. It's more dense. So because of that, we call this a thermally direct circulation. Warm air rising, cold air sinking. It's what you would expect. It's thermally direct. Now we're going to plot the isentropes on it. Remember, isentropes are a way of finding the front. And if we have this kind of circulation, the warm air is tending to get colder because it's rising, and air rising tends to get colder. Cold air is sinking, and when cold air sinks, it gets warmer. So what you're doing in effect is cooling the warm air and warming the cold air. That tends to kill the temperature gradient. Or if you like to look at the isentropes and actually think of those as physical surfaces, the cold air is kind of flattening, bringing them closer to the ground, and the warm air is bringing that squished area in the frontal zone higher up in the atmosphere. So in other words, it's trying to make those isentropes more horizontal. That's the case, then those potential temperature lines don't have a gradient anymore. And when the gradient dies, there's no front. In other words, the isentropes become more horizontal. So in the entrance region of a jet streak, it is frontolytic. In other words, it's causing the jet streak to slow down or die because of the loss of the temperature gradient. Now let's take a look at the exit region. In the exit region, you've got wind coming out and it's slowing down. Because it's slowing down, Coriolis force is pulling it to the south. And so you have cross-contour flow from the north to the south, in other words, from the cold air to the warm air. Because of that, you've got compensating motions down in lower layers of the atmosphere. You've got to the north, the air is rising, and to the south, the air is sinking. So let's think through this. Cold air, when it rises, of course, it expands and temperature decreases. So the cold air will be getting colder. Warm air sinking is forced to sink. Warm air doesn't normally want to sink, but as it sinks, it'll compress and get warmer. So this is what we call a thermally indirect circulation. Cold air rising, it has to be forced to rise. It doesn't want to rise by itself, so it's indirect. And warm air sinking, warm air doesn't normally sink by itself, so it has to be forced to sink. And we call that a thermally indirect circulation. This is in the exit region or the eastern part of the jet streak. So with that warm air sinking, you can think of it as actually, as it sinks, warm air gets warmer, and cold air as it rises gets colder. So to the north it's getting colder, to the south it's getting warmer. So this is enhancing the temperature gradient. Not only that, you can think of this, those isotropes, or those lines of potential temperature, as physical surfaces. And if you're pushing them down to the south and pulling them up towards the north, they're going to get more vertical or greater slope. In other words, this is helping a front form. It's frontogenetic. So in summary, in the entrance region, you have cold air sinking on the left rear, and you have warm air rising in the right rear. Now in the exit region, the left front, you got cold air rising, and the right front, you've got warm air sinking. So that means that in the entrance region of the jet streak, it's frontolytic, and in the exit region, it's frontogenetic. So that means that out ahead of the jet streak, the temperature gradient to the east is getting stronger. So that means that your thermal wind is increasing because the temperature gradient is tied to the thermal wind, which means that you're going to have a stronger wind at altitude. But in the entrance region behind the jet streak, it's frontolytic. The temperature gradient's getting weaker. That decreases the thermal wind. So the wind at altitude is weaker. So this is how jet streaks propagate. They're almost like, gosh, I'm trying to think of a good analogy. Maybe a tank. A tank has treads, and treads, help you propagate forward. So out ahead of the tank, you're putting down treads, and that's frontolytic or frontogenetic. It's forming a front. And on the back side of the tank, the treads are coming up, and that is where the entrance region of the jet streak is frontolytic, or killing the front, and as a result, causing weaker winds at altitude. So there's also preferred regions of surface development. In other words, at the surface, as a jet streak moves over the lower level low pressure system, it will intensify it wherever you have rising motions or divergence aloft. And that would be in the left front quadrant or the right rear quadrant. So that is the tie between surface systems, fronts, and jet streaks. And that's our current understanding of how weather systems develop.